Good evening and welcome to IPA50 webinar series New Horizons in Physics. We have 22nd lecture today, and today's lecture will be given by one of our very eminent scientists, Professor Bimla Buti. Professor Bimla Buti was awarded Indian Physics Association R.D. Birla Memorial Award in Physics 2020 in recognition of outstanding contributions in nonlinear dynamics and understanding of chaos and mentoring. Today, to coordinate the lecture, we have invited Dr. Sangeeta Bose. She is an associate professor at Mumbai University DAE Center for Excellence in Basic Sciences. She did her PhD at TIFR in the area of mesoscopic superconductivity, and recently she has ventured into area of organic electronic devices. She won the prestigious INSA Young Scientist Award in 2008 and was an Humboldt Fellow. I now invite Professor Sangeeta Bose to introduce today's speaker and conduct the lecture.
Good evening, everybody. So first of all, I would like to thank IPA for giving me this opportunity, and especially Vandana. So it's indeed a real honor to be introducing today's speaker, Professor Bimla Buti. Professor Bimla Buti has a long and illustrious career as a theoretical plasma physicist. She did her PhD from University of Chicago in 1962 under the guidance of Professor Chandrasekhar. After her PhD, she joined Delhi University and later IIT Delhi. She joined Physical Research Laboratory as a faculty in 1970. She was instrumental in strengthening the theoretical plasma physics group at PRL. Professor Buti also started a new section for the experimental plasma physics program at PRL, which later became the Institute of Plasma Research as we know it today. Between 1985 to 2003, Professor Buti was the director of plasma physics at the International Center for Theoretical Physics, Trieste. Professor Buti's work revolves around theoretical developments of plasma waves and instabilities. Her work on turbulence and chaos is globally acknowledged. She has several recognitions, like being the first woman fellow of the Indian National Science Academy and the Third World Academy of Sciences. She is also the fellow of the National Academy of Sciences and the American Physical Society. She has won many prestigious awards, like the Vikram Sarabhai Award for Planetary Sciences, 1977, the Jawaharlal Nehru Birth Centenary Lectureship Award, 1993, the Vaini Bapu International Award in Astrophysics, 1994, and the Lifetime Achievement Award of the University of Chicago in 1996. She initiated and founded the Plasma Science Society of India and worked there as its president between 92 and 93. Professor Buti has continued to inspire generations, especially women scientists. She has also initiated a range of awards through the Physical Research Laboratory and the Indian Physics Association. Besides science, Professor Buti is also a keen social worker. She has set up the Buti Foundation in 2003 and continues to work for social causes through this foundation. With this, I would like to invite Professor Buti to deliver today's IPA Birla Memorial Award 2020 lecture. One announcement I would like to make before I hand it over to Professor Buti is today's question answer sessions will be conducted. So we will be displaying the questions. So we would request everyone, both in the Zoom platform as well as in the YouTube, to please write the questions in the chat box. So we'll take the questions and then project it after the lecture. With this, I would invite Professor Buti. Professor Buti.
Thank you very much, both Vandana as well as Sangeeta, for your kind introduction. And as I show in this first slide, the topic on which I'm going to talk about is coherence and chaos in plasmas. But before I do that, I would like to express my sincere thanks to Indian Physics Association as well as the members of the selection committee of R.D. Birla Award who conferred this award on me. I would take this opportunity to express my gratitude to my guru, Nobel laureate, Professor S. Chandrasekhar, who gave me the training that brought me to the level that you see me today. I would also like to inform you that Professor Chandrasekhar was one of the earlier recipients of this Bimla Award. And that gives me a great pleasure and pride that the Shishya is following her Guru. I'm going to talk about the applications of the plasmas. First of all, the question one would like to ask, why do we want to study plasmas at all? You know, the plasma science provides one of the cornerstones of our knowledge of the stars, the interstellar medium, the galaxies, and all those things. Although it is often not readily apparent, plasma science affects our society in a variety of ways. Study of plasmas is not only to explore the beauties of nature, but also to find its benefits to the society. For example, we are looking for alternative energy sources, and the nuclear fusion provides us with one such source for producing the energy. And this has a big advantage that it is pollution-free. We also make use of accelerators for energizing the particle, especially, say, for finding out how the universe came about. But those accelerators are extremely huge accelerators, like the one we have at CERN. Whereas the plasma accelerators, I'll show you in a little while, that they are much smaller and smaller than the usual accelerators that we have. Besides these, plasmas provide us a number of technologies, really helpful technologies. So that's why I say that the plasmas are useful for our day-to-day life. For example, as far as the technology is concerned, they provide us a means of controlling the environment pollution, for controlling the drinking water pollution, for managing the hospital and municipal waste, and many more. But I would just spell out a couple of medical applications. They give us a faster control of the intensity of the blood clotting. They also give us a tool for faster healing of the wounds by means of plasma torch. For dentists, they can provide cold plasma jets which kill the dental bacteria, which causes the tooth decay, but at the same time try to save our teeth. Here, I have not written down the applications for cancer patients, but it has a big advantage. What we do is we produce the nanoparticles by means of plasmas, and then the medicine is injected through these nanoparticles locally, where the cancerous cells are seen. The big advantage is that it kills only the cancerous cells and not the healthy ones, unlike the other devices which are available to us. Okay, now let me go to the topic of discussion for today. You know, both the coherence as well as chaos are manifestations of non-linearity in the system, under the system that we are considering. There's no possibility of having either of the two in a linear system. In plasmas, unlike the ordinary cases, collective effects play a very important role. And these collective effects give rise to a variety of waves and plasma instability, as mentioned by the introduction given by Sangeeta. Some of the waves that I'm going to talk about today are the Langmuir waves, which are electrostatic oscillations of high frequency. Then we have the ion acoustic waves, which are low frequency waves, where the ion dynamics plays a very important role. Many times, we have plasmas which are embedded with magnetic field. In such plasmas, we can have another type of waves called Alfven waves. And we will talk about these one by one. First of all, I'll give you an example of plasma waves in our Earth's magnetosphere. You know, when we have the charged particle coming from the sun in the form of a solar wind, this cannot penetrate us directly because of the presence of the Earth's magnetic field. It has to cross the magnetosphere. The plasma magnetosphere is formed, and the construction, the different sheets that we get in the magnetosphere are shown here. And we find that there are a number of waves which have been observed in this plasma that we are talking about. We do see these waves in the magnetopause and also in the plasma sheet boundary. For magnetopause boundary layer, they play an important role for the entry of solar wind plasma into the Earth's magnetosphere. Plasma waves indeed provide the dominant loss mechanism for energetic electrons in the inner magnetosphere, and they act as drivers for precipitation of ions and electrons into the lower atmosphere. I show you another beautiful example that when these charged particles coming in the form of a solar wind, when they collide with the molecules in the Earth's magnetosphere, molecules get excited. And then these molecules, when they calm down, they create rippling curtains of color, as shown in this figure here. Different molecules result in different colors. And for example, oxygen gives rise to green and yellow. The nitrogen molecules will give red, blue, and purple. The colors of these northern lights, as they are called, are also affected by the altitude. The slide that I am showing you of aurora here, this is from Alaska in United States. I was fortunate enough to observe this aurora at Alaska. I had gone to Geophysical Research Institute at Fairbanks in Alaska to give some lectures, and my host was kind enough to give me a car and ask me to drive almost another 200 miles north to see such a beautiful aurora. The one I saw was certainly not as fantastic as you see in this slide, but it was certainly mind-blowing. That was a great thing that I could see. Now, let's come to the study of nonlinearities in plasmas. Some nonlinearities can lead to even new plasma instability that in turn can lead to coherent structures like soliton, turbulence, and chaos. All these have been observed both in laboratory as well as natural plasmas. To start with, for coherent structures, let me start with the simplest example of laser plasma. We all know that laser is nothing but coherent stimulated emission of light. Here on the right, I'm showing you that ordinary light is a scattered light, but the laser light is coherent and we get the focused light. The plasma can be produced by providing the sufficient energy to ionize the atom through various means. Plasmas can be created by means of high-power lasers. They can also be created by means of energetic particle beams. And there are many other ways of creating plasmas. I also briefly mentioned about the laser plasma acceleration. And as I pointed out, these accelerators are not only high-performance particle accelerators, but at the same time, they are of much smaller size than the conventional ones. And here I'm showing you a slide which shows us what happens when the laser pulse is shining. Here is an example of a small size laser plasma accelerator. On the right, I'm showing you what type of particles and what type of rays the plasmas which are produced by lasers can be emitted. Let's go to the next coherent structure called solitons or solitary waves. And in fact, the solitons are stable solitary waves. Historically, solitary waves were first discovered by John Russell Scott in 1834 when he was riding a horse along the shore of a canal. He observed a solitary wave that did not change its shape even though he rode miles and miles. A solitary wave or a wave packet that maintains its shape while propagating at a constant speed. On the right, I showed you a solitary wave, and here we have a carrier wave whose envelope is a soliton. Now, you may ask me the question, how are they produced? You know, in a dispersive medium like plasma, solitons occur when the non-linear effects balance the dispersive effect. Plasma is a dispersive medium, and I also showed that non-linearity are very essential for giving rise to these coherent structures. During the interaction of the soliton with other solitons, they maintain their shapes. At the most, they might change their faces. And here I'm showing you a small video where it is showing the interaction of the two solitons, but after this interaction, they come out clean as they were. Here I'm showing you another slide where we find that the envelope soliton, as it evolves in time, does not change. It remains exactly the way it was to start with. On the right, I'm showing you the head-on collision of two envelope solitons. After passing through this interaction region, you find that the two solitons have exactly the same shape. And in this particular case, even the phase has not changed. The next question that one would like to answer, how are they produced? Are there any mathematical equations which tell us that we will face such solitary waves or solitons in plasmas? The answer is yes. Here, I'm giving you the evolution equation for the plasma waves in the liquids, the waves in the liquids, water waves, and also the ion acoustic waves, which are small frequency waves. They are governed by an equation shown here. I'll show you a few equations, but without going into the detail, for the simple reason that the organizer had requested me to tone down the level of my talk so that the teachers and the students from colleges can get what I'm talking about. So I'll try to do that. This nonlinear equation was independently derived by two scientists, Coherent and Devery, and it is called Coherent-Devery equation or the KDV equation. So even though it's a nonlinear equation, we can solve it analytically, and the solution turns out to be the one given here, where U is the amplitude of the soliton. And this hyperbolic square solution represents the solitary wave. The figure on the right that I am showing is for the solitons or the solitary waves which have been observed in the Andaman Sea of Indian Ocean. And we believe that in this Andaman Sea, we see extraordinarily large internal solitons. Now, what's going wrong? Okay, the next one that I'm going to show is that I talked about Langmuir waves. We will try to figure out what is the equation that governs these weakly nonlinear Langmuir waves in plasmas. And we come up with this equation. We start with the fundamental magnetothermic equation, and by using the perturbation scheme, but not the regular perturbation scheme, but the singular perturbation scheme, we come up with the equation given here. If this nonlinear term was not there, you would immediately recognize that this equation is nothing but the Schrödinger equation that we studied in the very first course in quantum mechanics. But the presence of this nonlinear term makes our life much more difficult. This equation provides us with two solutions. This can be solved analytically once again. One solution, when kappa is a positive quantity, gives us the envelope soliton, sometimes called the bright soliton, which are shown in red here. The solution of this, which I'll show you in the next slide, in the form of hyperbolic set, and that is the shape that it has. For kappa less than 0, it gives us the solution in the form of envelope holes, sometimes called the dark solitons also. These solitons we get because this one-dimensional nonlinear Schrödinger is an integrable equation. For any equation which is not integrable will not give rise to the soliton solution. You may immediately ask me the question, what are the integrable systems? A system with n degrees of freedom is integrable only if it has n constants of motion. And these constants of motion are in involution. That is, they satisfy this equation, where the curly bracket is the Poisson bracket. Now, what happens if our system is governed by Schrödinger equation, which is not one-dimensional, but say three-dimensional? I will show you what the three-dimensional nonlinear Schrödinger equation is. All I'm trying to tell you that the nonlinear Schrödinger equation is not integrable, and it would not allow the solitons to exist in that system. It will take us to a phenomenon of chaos in the system. Let me show you how. This is the evolution equation for the system which desire that we take into account the three-dimensional quantities. Okay. For a spherically symmetric case, this can be reduced to a much simpler equation, which looks like the one-dimensional nonlinear Schrodinger equation, but that is not quite so, because this is not integrable equation, and this does not give rise to the soliton solutions. Then what? Then, as I mentioned, that we get what is known as the collapse in the plasmas. Phenomena of collapse in gravitational system is rather well known. White dwarfs, neutron stars, and black holes are beautiful examples of this collapse. In plasmas, by collapse, we mean that the size of the three-dimensional density depletion, which are called cavitons or clumps, they reduce to the size of Debye radius. By the way, Debye length is characteristic length of plasma. When the collapse takes place, the trajectories of the particles start interacting and the wave energy gets dissipated. So collapse offers an efficient nonlinear dissipation mechanism. Existence of such cavitons has been demonstrated both by experiments and by numerical simulation. We have also shown that the plasma governed by 3D nonlinear Schrodinger equation undergo similar collapse, but under some restricted conditions. It was Zakharov, the very well-known Russian scientist, who studied the time evolution of spherical 3D Langmuir waves in strongly turbulent plasmas. And he showed that in finite time, these Langmuir waves undergo the phenomena of collapse. And he claims that they always undergo collapse. However, somewhat later, in 1977, we showed that the claim made by Zakharov is not exactly valid. For the simple reason that the approximation made in Zakharov's model, they break down when the collapse takes place. Zakharov had taken one type of nonlinearity in the system, that is the Pondor motive force produced nonlinearity. But we showed that when the collapse occurs, the other nonlinearities become equally important and sometimes more important than the one Zakharov had considered. For the details, I would suggest that you please refer to my papers. At the end of this talk, I'll give you a list of 2 slides giving the references to the papers which I have used for this presentation. I briefly mentioned about the magnetoplasma, which exists in most of the space and astrophysical plasmas. In such magnetoplasmas, a variety of large amplitude nonlinear waves have been observed. Nonlinear large amplitude Alfven waves have been observed by a number of spacecrafts. We are trying to talk about the phenomena of coherence and chaos. You might immediately ask me, do such phenomena of chaos and coherence occur when we talk of magnetoplasmas which show the presence of Alfven waves? The answer is yes. I show you the beautiful example here. Example of the great red spot of Jupiter. you see the coherent structure, which is the great red spot. The rest of Jupiter is turbulent and chaotic, but this is absolutely coherent structure. I'll come back to this later on when we discuss the phenomena of chaos. We talked about the evolution equations for the solitons in plasmas without the magnetic field. But when we have the magnetic field, and as we claimed that we can have Alfven waves which have been observed, the evolution equation for these weakly nonlinear Alfven waves is once again derived from the fundamental magnetohydrodynamic equations. For the derivation, please see my references. The evolution equation turns out to be of this form. You might immediately jump and say, well, this is nonlinear Schrodinger equation. But that is not so. It looks like nonlinear Schrodinger equation, but the nonlinear term here has an extra derivative, which was missing in the nonlinear Schrodinger equation. This equation is known as the derivative nonlinear Schrodinger equation, which governs the magnetic field. But mind you, this governs the circularly polarized Alfven waves, where B is defined by a combination of By and Bz, giving the circular polarization left hand and right hand. Fortunately, this can also be solved analytically, and the solution turns out to be in this form. I would like to stress upon the fact that the solitons given by this expression, they move with constant speed, which is characteristic of some of the properties of the plasma in which we have these Alfven waves. The plasma that we have considered and the wave equation that we have shown which governs them is a uniform plasma. That is, the density of the plasma is constant, homogeneous plasma. But very often we find that the plasmas in space and astrophysics are not uniform. They are inhomogeneous. We rederive the equation for that and solve it. Once again, we find that we do get the soliton solution, but in those inhomogeneous plasmas, they do not move with constant speeds, but they are accelerated. And these accelerated Alfven solitons can give rise to anomalous heating. We propose that this anomalous heating can be a source of coronal heating. You will be surprised to know that till today, we have not been able to find out the exact cause of coronal heating, because under normal circumstances, one would have expected the corona temperature would be smaller than the core temperature, would be smaller than the photospheric temperature. But instead of going down from 6,000 degrees, which is a photospheric temperature, the coronal temperature goes up. It's of the order of 1,000,000 degrees. I'm not claiming that this is the only source, that is the Alfvenic waves that can hit the coronal plasma. There can be a number of ways in which the corona can be heated. So far, we have talked about non-relativistic plasma, but we do have relativistic plasmas. What happens? Can we have such nice structures like soliton in relativistic plasmas? And I'll give you one of the examples for that. We are going to talk about the Langmuir soliton in relativistic plasmas and try to show you that these relativistic Langmuir soliton can be a source for radio pulsars. Here I'm showing you the picture of a pulsar with magnetic axis and the rotation axis. You know, the pulsars are nothing but rotating neutron stars. Periodicity of the pulsars is due to rotation of neutron stars, which have strong magnetic fields of the order of 10 to the power 12 Gauss. And these rotating magnetic fields, according to Maxwell's equations, give rise to macroscopic electric fields. And these electric fields, in turn, make the plasma surrounding the neutron star relativistic in a very short time due to the turbulence heating. In such relativistic plasmas, we have shown that Langmuir soliton can exist. These radio pulsars have very high temperatures, brightness temperatures. And these high temperatures can be explained only by means of a source like a soliton. And we have not only shown that the relativistic Langmuir solitons can occur in the turbulent plasmas in the vicinity of neutron stars, but we have also shown that they radiate coherently. So such coherent radiation can give rise to the radiation emitted by radio pulsars. Here I'm showing you what happens when we have the turbulence that I talked about in the neighborhood of our neutron stars. Here I'm showing you some simulations which show that the electrostatic potential in turbulent state shows a mixture of coherent structures as well as the wave fluctuations in the rotating fluid with magnetic field like the one we have in the vicinity of neutron stars. Now I would like to give you some examples of the coherent radiations emitted by the soliton that we have been talking about. I'll give you 4 examples, and they are the ones that we have worked upon. First, I take the case of kilometric radiation, which is observed in our auroral plasmas. I talked about the beautiful auroras earlier. We have proposed a model for the generation of strong electromagnetic radiation from the nonlinear interaction of Whistler solitons with upper hybrid waves. We have applied this model to the generation of auroral kilometric radiation known as AKR on the auroral field lines in the Earth's magnetosphere. The power we find is larger in the plasma depletion region as compared to the high density region. Our theoretical prediction agree very well with the observed properties of AKR. For example, the observed frequency, the observed polarization, the observed peak power, and its tendency to occur in the density depletion region are well taken care of by our model. Next example that I'm going to talk about is about the solar radio bursts. A variety of solar radio bursts have been observed. Here we'll be talking about 2 type 4 solar radio bursts, one which is a moving type and another one which is a stationary type. We show that the type 4 moving bursts occur when the interaction of Whistler solitons and upper hybrid waves takes place in the coronal transients, whereas the type 4 solar bursts originate provided the interaction takes place in stationary lobes where the density is large. It's a beautiful picture which shows the coronal lobes and the coronal chambers giving rise to the solar wind. I have taken this picture from Insights. Two more examples that I'm going to talk about are the coherent radiation from comet Halley. The large amplitude electromagnetic turbulence and plasma waves have been observed in the vicinity of comet Halley. This turbulence can lead to envelope Alfven solitons. We have proposed a mechanism involving nonlinear interaction of Alfven solitons and Langmuir waves to explain the cometary kilometric radiation called CKR. We observe in the vicinity of comet Halley that is going through this phenomena of Alfven solitons, envelope solitons. According to our model, the frequency of the radiation emitted depends on the position of the interaction region relative to the comet. Higher frequencies are emitted when this region is closer to the comet. The CKR source is shown to lie at a distance ranging between 10 to the power 5 and 2 into 10 to the power 6 kilometers from the comet nucleus. Several observed features can be explained in our model. Next example I would like to give you is that of bursty radio emissions from Uranus. Just like the kilometric radiation that has been observed in auroral plasmas in our Earth's atmosphere, auroras have been observed in Uranus as well as in Jupiter. Here we are going to talk about Uranus. The distribution of energetic electrons in the magnetosphere of Uranus can develop large anisotropy and a large loss scope. These in turn can lead to large amplitude Whistler waves and upper hybrid waves. Nonlinear currents caused by the interaction between these waves can produce radio emissions that are in good agreement with the bursty Uranian kilometric radiation, which is observed by the spacecraft Voyager 2. Here is the two tails of the comet. One is the dust tail, another is the gas tail, the plasma tail that we are talking about. Now we are going to talk about the chaos in a system, chaos in plasmas. First question that comes to my mind is to find out, is there any relation between chaos and turbulence in a system? You know, the plasma turbulence is related to ordinary fluid turbulence, but is more complex because of the plasma particles having interaction through the long-range Coulomb forces. Chaotic system is essentially a turbulent system, as vice versa may or may not be true. That is, the turbulent system may be chaotic, may not be chaotic, but a chaotic system is always turbulent. And we do see turbulence in everywhere, almost. We fly in the airplane, and very often we hear the pilot announcing, please put on your seat belts, we are going through a turbulence. Chaos cannot be equated simply to disorder. Chaotic regime is not just one continuous regime of irregularity. In plasma, it is. But in chaotic regime, it is not one continuous regime of irregularity. I'll show you a little later that it can contain windows of order within disorder. Then how do we really define a chaotic system, which is showing the characteristics which are quite different from a turbulent system? Let me admit that there is no unique definition of chaos. The simplest way it can be defined is as follows. If we map the trajectory of a particle in a given field, and if the trajectory is not smooth but scattered, then the system can be chaotic. It may be, it may not be. The scattered mapping, in fact, is a necessary but not the sufficient condition for the system to be chaotic. There's another condition for a system to be chaotic, is its extreme sensitivity to the initial condition. That is, the two neighboring trajectories with slightly different initial condition must diverge exponentially. These are just the qualitative definitions of a chaotic system. But how do we find out how chaotic is a given system? Is there anything that will define this for us? Yes. We can get the quantitative estimates from what is known as Lyapunov exponent, which is defined by this simple relation, where d is the physical distance between two neighboring trajectories in phase space. It turns out that the Lyapunov exponent, if it is positive, then that satisfies both conditions. It is necessary as well as the sufficient condition for the chaos to take place. Lyapunov exponent sort of quantifies the average exponential rate of divergence of neighboring trajectories. This plays an extremely important role in the discussion of chaotic system. We'll make use of this in the following slides. Historically, Jules Henry was the first person to recognize the chaotic behavior of a dynamical system. He encountered this behavior, unexpected behavior, in his studies of three-body system in planetary system. And here is a picture of Sun along with its planets. I would like to emphasize on the point that the minimum number of degrees of freedom of a dynamical system like the one we are considering, the system needs to have 3 degrees of freedom. Only then it can be chaotic. And we'll give you a proof of this. The simplest example that I can give you of a chaos is the driven pendulum. The simple pendulum when it is driven by some driver, independent of whether it's a simple driver or what sort of a driver. In the absence of a driver, the pendulum has single period, but at a certain point, it becomes double. The period becomes double. This is called period doubling bifurcation. At another point, you find another period doubling bifurcation. And so is the case here. Through a sequence of such period doubling bifurcation, the system goes into a chaotic state. This is known as period doubling route to chaos for a driven pendulum or an oscillator. We'll use this analogy a little later. We talked about the Alfven waves which have been observed, but very often we find that we cannot express our given system, our magnetoplasma, by means of the evolution equation that I had shown you earlier in 1 dimension or 2 dimensions. In realistic 3-dimensional system, we have re-derived our equation for the nonlinear Alfven waves, and it turns out to be a vector equation shown here. This governs the electrically polarized Alfven waves. Unlike the earlier cases, this cannot be solved analytically. It can certainly be solved numerically, and we have done that, and I'll show you very briefly the results for the numerical solution. But we try to figure out how much more information we can get out of this, what sort of special cases that we can consider, which we can get analytically. One case I have already shown you is that if we are satisfied with circularly polarized Alfven waves, then this equation reduces to the one which I showed you in one of my previous slides, which has a solitary wave solution, the soliton solution. One more thing that we can do with the vector equation is that the localized stationary Alfven waves can be governed by this set of equations by making simple transformation for the localized stationary waves. Then we show that the vector equation, complicated vector equation, can be given in terms of these 2 equations. For details, please see my reference given here. In that case, we find that the Hamiltonian of the system, which is quite complicated, so I have not shown you the form of the Hamiltonian, but all I would like to say is that Hamiltonian is chaotic in B, the magnetic field. it has a minimum, it has a maximum, and a double root called the saddle point here. Here I'm showing you in phase space the constant energy orbits. The orbits here around the minimum of the potential H, they are the dark solitons. The dark because the magnetic field for these solitons is smaller than the ambient magnetic field. These dark solitons have right-hand polarization. Outside, we get the bright solitons where the magnetic field is large compared to the ambient magnetic field. These bright solitons have left-hand polarization. We also see third type of solitons, the banana type orbits, which have mixed right-hand and left-hand polarization. Now, these orbits do not interact with each other. So there is absolutely no chance of getting any interaction, any scatter, and consequently any chaos in such a system which is governed only by 2 degrees By and Bc. What happens if we drive these waves that we are talking about by some driver? This may be an external driver, or maybe when we are talking of these waves in natural plasmas, there exists another wave which interacts with these waves and acts as a driver. Here I am showing you the results of these waves under the influence of a simple harmonic driver of frequency omega. All I would like to say that this time the system is governed by a set of 3 equations with 3 degrees of freedom, By, Bz, and theta, which comes about only because of the driver. And as I mentioned in the beginning, that if a system has minimum 3 degrees of freedom, there's a possibility of system becoming chaotic. Do we see chaos in such a system? The answer is yes. Here, I'm repeating the figure that I showed you in the previous slide when there was no driver. The amplitude of the driver was 0. When we switch on the driver, for very, very weak drivers, the scatter starts appearing in the vicinity of the saddle point. I'm not showing you those figures in between, but when the driver is somewhat stronger, the amplitude is 0.3, then the system is completely chaotic system. In this, we have shown only the Poincare points and not the Poincare orbits. I would also like to find out, does these drivers, their polarity, the polarization, would that make any difference to the stability of the system? I'm showing you that the answer is yes. On the left-hand side, we have taken a left-hand polarized driver. When the driver is extremely weak, as I mentioned earlier, the scatter starts in the vicinity of the saddle point. The scatter increases as we increase the strength of the driver. When it is further increased for amplitudes of the driver, say about 0.2, the system becomes completely chaotic except for this region. And mind you, what is this region? It is this region, which corresponds to dark solitons which have right-hand polarization. And I told you that the left-hand side figures correspond to the left-hand polarized driver. To make sure that what we are seeing is clearly because of the fact that the left-hand polarized driver does not like to interact with the right-hand polarized soliton. They are not touched upon at all. And to assure you that the statement that we are making is true, we have repeated our calculation for the right-hand polarized driver. And lo and behold, the region which was untouched upon becomes chaotic. This is what we call coherence in chaos. And I have shown you earlier the beautiful example of red spot Jupiter, great red spot of Jupiter. The rest of it is turbulent and chaotic, but this is coherent. I would also like to show you that supposing we are working in laboratory plasmas and we find that certain region is chaotic, turbulent, we would like to find out, is there any way to reduce the chaos or to get rid of the chaos in that region? And I'm going to show you by showing you two examples in this slide. On the left-hand side, I'm giving you the example of cometary tails. The earlier, we had considered only two species plasmas like hydrogen plasma with electrons and protons. But here we are talking of the heavy charged particles in the cometary tails along with the electrons and protons. So we have three species. So we got to go back and derive the equation for multi-species plasma. We have done that. And in the case of cometary tails, we show that for the strength of the driver, which had become completely chaotic at the amplitude 0.3, is absolutely non-chaotic now. We have to make the driver much stronger, the amplitude, say about 0.8 in place of 0.3, and still we see only the chaos has started taking place, but still we have many periodic orbits. We give you another example of Saturn rings. The ions are much heavier in this case. And we see that even though the driver is extremely strong, we start seeing the appearance of chaos in the system. So we certainly have a way to reduce the chaos in a system or sometimes eliminate the chaos in a system. Earlier I talked about in case of driven pendulum. I showed you that we can get chaos by what is known as period doubling route for chaos. In these plasmas that we are talking about, is there any way, any other channel through which we can get chaos? We are talking about the chaos produced by Alfven waves. And I'm going to show you that if we have a dissipative system, in a non-dissipative system, which is governed by Hamiltonian, the phase space does not change. It does not shrink. But in a dissipative system, the phase space shrinks. And it can shrink to a point, to a line, depending on the dimensionality of the system. And these are what are called as the attractors of such normal system. In a chaotic system, however, we can get an attractor which has complicated structure. And on top of it, it has fractal dimension. It doesn't have integral dimension like 0, 1, 2, etc. This is called the strange attractor. That is characteristics of a chaotic system. And we show you that the vector equation, nonlinear equation that we have derived, we have solved it numerically. And we see that the chaos comes through a period doubling bifurcations shown in the upper figure. And we show that there is also a possibility of going into chaos all of a sudden. On the top, the numbers that I have given correspond to the strength or the amplitude of the driver. And you see that chaos occurs at label I. And I have shown you that I is nothing but the strange attractor. So we see that the chaos near the minimum of the potential goes into a chaotic state only because of the strange attractor. The sudden transition is simply because of the strange attractor. You may ask me, can I claim that this is a strange attractor? The answer is yes. We have calculated the dimension of this strange attractor and it turns out to be 1.57. This brings us to a very fascinating subject of fractals. I'm trying to show you the existence of fractals which are related to the phenomena of chaos that I have illustrated. And these fractals are very useful because they have the self-similar property. And because of the self-similar property, if you change the size of the system, the properties don't change. So we have made use of, not only we, but the engineers have made use of the.
Oh, we lost her now.
Yeah, connection has gone, I think. I think the power has gone in her house.
Yeah, that's what I felt. But she's still logged in.
And now she's come back.
Okay.
Of the fractals in the antennas. And these small size antennas are used in our mobile phones and also in communication. So these are some of the advantages that we see of fractals. And fractals are found in plenty in nature. I would like to summarize by saying that I have tried to give you the overview of the subject of chaos and coherence that does occur in natural plasmas. And it can explain some of the intriguing observations in natural plasmas. Unfortunately, I could not go into the details of discussion of fractals. And these, the phenomena of chaos as well as fractals, they are found in biological systems also. They have practical applications to artificial intelligence. I wish I could show you those slides, but I will manage without that. And I would like to show you some of the slides, if possible, later on, which gives all the references to the papers that I have used for preparing my talk this afternoon. And I would like to stop my talk by expressing my sincere thanks, both to the audience as well as to the organizers of this lecture, especially Dr. Vandana Nanal. Thanks. Okay.
Many thanks, Professor Buti, for a very excellent talk on the instabilities in plasma leading to turbulence and chaos. So we'll take few questions. Screen visible, ma'am?
Yes.
I can see it, yes.
So the first question is by Krishna Chandra. Wants to know whether we can get some examples which are turbulent but not chaotic.
I wish I had my slides. I had examples of turbulent plasmas which are non-chaotic. You see, as I mentioned, the chaotic systems must satisfy certain conditions, like the Lyapunov being a positive quantity. But the turbulent system cannot, don't have to satisfy such a condition. What you see is the disorder completely. That is what you see in turbulent plasma, both in fluid plasmas as well as the plasma in turbulence in plasmas that we have talked about. I only wish I could show you the slide. The next question I see is not a question.
So the others are basically comments. So I'll just take the questions from from Zoom.
Radio emission from pulsars due to Langmuir solitons in the plasma. Can effects of instabilities in plasma turbulence on this emission account for glitches or anti-glitches?
The last part is not clear.
Effect of instabilities in plasma turbulence on this emission, that is on the pulsar emission, can it account for glitches or anti-glitches which are observed?
He's asking whether we can take care of the inhomogeneities as far as Langmuir solitons are concerned. Is that what he is asking for?
I think so. Is the instability of plasma turbulence responsible for the glitches?
Yes, that is exactly what I said. For example, when I was talking about the relativistic Langmuir solitons, we found out that in the vicinity of the neutron stars, because of the rotating magnetic field that can give rise to the strong electrostatic fields. And these electrostatic fields can give rise to the turbulence. And again, because of this turbulence itself, we get the nonlinear Langmuir solitons that I have discussed in my lecture. And they do give rise to the emissions which are coherent that I talked about in connection with the pulsars or
Okay.
radio emissions.
Okay.
Annie Joseph is asking, is it right to say coherence are linear and chaos are nonlinear? No. The answer is no. As I said right in the beginning, both coherence and chaos are manifestations of non-linearities in the system. In a linear system, you would neither see chaos nor coherence. When I say coherence, I told you about coherent structures, coherent radiation, coherent structures like solitons, etc., etc. You will never see them in a linear system.
Okay, so thank you, ma'am. The second question is from Deep Kumar. Can a soliton survive in a chaotic environment?
Yes and no. Soliton can't survive as a soliton because for soliton, as I showed, that the solitons that I have been talking about are in one dimension. They are the ones which survives as such. But when we go over to the higher dimension, this one dimension solitons that we talk about are certainly good, supposing we have a system in a magnetic field. And if the magnetic field is very large, we will find that mostly the propagation is in one direction. So you can certainly get soliton. But when I showed you, if we go to higher dimension, some of the solitons, especially the language solitons I talked about, they cannot exist. They go through a collapse. They become three-dimensional. You may call them three-dimensional soliton, but I would not like to call them soliton because solitons, by definition, are the systems which are coherent structures, which do not change even when they interact with other solitons, etc. So in chaotic system, solitons will not exist as soliton.
Thank you, ma'am. So I think Vandana has already prepared the slide with Zoom questions. She will just now project. So I will stop sharing. Thank you, ma'am. Yeah, Vandana, go ahead.
See the question.
Yes, okay, please.
For driven plasma with heavy ions, can one avoid chaos with very small fraction of heavy ions? This is a question that can be answered by going through the details mathematics. One cannot right away make guesses whether it can be done or not done. Firstly, it will depend how heavy the ions are. As I showed you the two examples for the cometary chains, there also we had taken heavy charged particles, heavy charged ions, but the system required the drivers which were less in strength to bring in the stability. Whereas for the Saturn rings, where the ions are much heavier ions, we required much stronger drivers. So it will depend on what sort of plasma you have and the heavy ions that you are going to introduce, how heavy they are. Or it will certainly depend on that. And then only one can say that what fraction of heavy ions will give rise to the removal of the chaos or reduction of the chaos. Now, I have one more question here. Is that from you or from one of the participants?
No, it's my question.
Can you give one or two examples of fractals in biological system? Yes. In neural networks, in artificial neural networks, we use fractals. What do we do? What do we mean by neural networks? These are computer software programs which try to mimic the real working of the neurons in human brains. So once you have created neural networks, then come into the picture of this introduction of fractal nature. And they make it much more efficient, these computer systems that we are talking about. And those are being used in artificial intelligence now. But the field is completely open. And in fact, as I mentioned, especially the young students in the virtual audience that we have, if they want to go for research, they can jump into this field. It's wide open. Both the techniques that I have given you for the study of chaos in the system, that is the Poincare maps, is good for studying any nonlinear dynamical system. You may be surprised that human heart is a dynamical system. So that can be described completely by the tools that I have used for describing the chaos in plasmas.
Thank you.
Have I answered your question?
Yes, and you answered the next one as well.
I have already given advice to the young students.
Yes.
That they should jump onto this opportunity.
Yes.
In nature, there are many examples. I'm just showing you 4 of them. They are all fractals. You change, you cut them, still they maintain their form. How beautiful they are. Okay? And the summary I have already given you. And the 2 slides where I have given the references to my papers, which have been used to prepare this presentation. Okay? That takes care of it.
Okay, thank you very much. I'll add your email address to the information.
Great. Thanks a lot.
Thank you. Thank you.
They can send me email.
Okay. Yeah. So actually for the people who are on Zoom, just hang on. I will put the email address here right now.
In between.
Yeah, I have put the address at both YouTube and the Zoom chat. So they have your email address. Okay, thank you very much, and thank you all for joining us. Thank you, Professor Bimla ji and Dr. Sangeeta and all the audience, and I hope to see you all again next week. See you then. Bye-bye.